Welcome to After Hours Engineering. We need a way to interact with our SoC, and the most common way to do that is via a UART. In this episode, we're going to wire up a very minimalist UART component, and more specifically, wire it up such that we interface an 8-bit bus to our Femto's 32-bit bus. Along the way, we'll encounter a few hurdles and gotchas and hiccups, but nothing that we can't solve. So let's go. Let's start with the diagram of the UART component. This is a new component, our very first component that we're going to add to the system. It's going to give us the ability to talk to an outside world via a bit stream, in this case the UART protocol. The thing is that the UART is an 8-bit device and we need to interface it to the Femto, which is a 32-bit data bus. So we need to translate 8 bits into 32 bits or 32 bits into 8 bits. And I'll show you that in the code in a minute. Now, like all components on our very simplistic bus, we need to follow this particular structure right here. We need to at least have a reset, a chip select clock, and read strobe, read, and then an address. The UART itself is really simple. It just consists of a couple of buffers, a few buffers inside here, a control buffer, a read buffer, and a transmit that are hooked up to the receiver and the transmitter. Now we use buffers here such that when a byte comes in, we load it into the buffer here, and then the component or the system, the Femto, can come by and read it whenever it likes. If another buffer comes in, then we ignore it. And the same thing for the 32 bits. If the processor wants to send 8 bits or a byte, it needs to transmit it in here and load it into the buffer right here. Now, each one of these buffers has an address, 0, 1, and 2, and we'll see how that address is formed inside of the SoC itself. So this particular component will sit inside of the SoC, and this is the only outside connection to the world that we have. In this case, it'll be to a USB to UART connector. So this is the diagram. So our goal will be to set up the correct address that'll select one of these buffers and then read or write, poll, if you will, on one of these control bits. For example, if a byte has come in, it will set one of the bits here saying that there's a byte available. Our software will sit there and read this control register and mask it with some sort of mask until that bit flips to a high, and then we know that a byte has come in. And the inverse is also there, where we write a byte to here, it sets a bit here, and we can tell when the byte has been transferred because this component will set that bit high, and then our processor will know that it can write another byte to the buffer and transmit again and go around in signals, transferring one byte at a time. And that's the diagram. So where does the UART component sit within the SoC itself? So over here to the left, we have a bigger picture of the entire Schoko. We have our Femto CPU, the port A buffer, and the UART component itself sitting within the SoC. The SoC is enclosed within the top module that interfaces to the real world, the LEDs themselves, and our USB component that we have over here. Now, all of that matches up with the physical world, which is right here. This is that USB to UART right here. That's what this is. This is the LEDs port right here. And over here is the Schoko itself, and there is the LED. And then finally we use our Tiger over here, our Tiger, to upload over the FPGA wires and onto the board itself. That's where the component sits. Next, I want to talk about a slight hack that I made to the Femto processor. I don't think I need this, but it does solve my issue for the moment. So if we take a look at what that was, I've added this signal right here called mem access. Come down to its definition, it goes high whenever we're doing a load, a store, or we're in the fetch state. And the real question is, why did I add this? And I really don't think I need it, but for now, I'm going to keep it until I can address it. What was happening is if we look at this little example here for this assembly program, what was happening is that when we had a branch backwards in the instruction, the address register actually contained the instruction itself, and it was causing my SoC to inadvertently activate I/O, which wasn't good. Now, I think I know what the fix is, and I can get rid of this, but in terms of recording this episode, I'm going to stick with why this is in here. And so you'll see in the SoC in a minute that I actually check this mem access. And of course I shot myself in the foot later on when I realized that I had a typo in there, so I doubled up my problems. But that's why we made a small change to the Femto. I'm pretty sure I can remove this. Next we need to look at how the memory mapping works in conjunction with the SoC and the Femto. And keep in mind that our UART component is an 8-bit component, but the Femto is a 32-bit component. So first off, I'll talk about how I granularize the whole thing a little bit more. The entire word shows out as an internal address that you can drive to your component. So your component could have up to 256 addresses within it. And then which device you're selecting, we only have 2, the UART and port A, but you could have 256 of those as well. And then the I/O select, which is driven off of 1 bit, and you're selecting RAM or I/O. So when this bit is high, which means it's a 4, 0, 1, 0, 0, you get the I/O. Now, the question is that our UART component sits in the memory address space, and there's at least 2 different ways you could do this. You could have your component, all of its registers, if you have 4 of them, sit in a single word. I didn't go that route. I put each one of the registers in their own address word right here. So 0, 0, 0, 1, or 2, and then a 3 will access each one of these different registers, either writing to them or reading from them. Now the thing is that this adds a little bit of glue logic so that you properly read from this registers and correctly align them with the address in which they are. And I'll talk about that in a second. And it comes down to what the Femto is doing. So over here to the right, we can see what the Femto is doing in terms of loads and stores. The first thing it's going to do is look at the instruction to determine whether it's doing bytes, half words, or a full word. And this is like a waterfall. After we've determined that, we can determine what our load sign is, the actual loading data. In this case, we're just looking at the load right now. So it'll determine, oh, we need a load byte or a half word to be placed into our half word access or byte. The half word itself, the load half word from up here, is defined by the load address bit 1. That's these 2 little bits right here in our address space. They're determining which piece of the 32-bit word we're going to pull from. So for a half word, you're either pulling from the entire low 16 bits or the entire upper 16 bits. If we're doing load bytes or store bytes, doesn't matter, we're just looking at the load right now, then we'll look at only the lower byte or the upper byte of the half word itself. So you can see that we're cutting space in half as we move down this tree. And the storage is almost identical, other than we're dealing with a mask. So we need to set up our write data based on our load store address. And it's again looking at the lower 2 bits of the address right here to determine what it's trying to do. If it's doing a byte, then this will be 0. If it's doing a half word, then this bit goes to 1. Again, we're up here looking at that. The other thing is how we want to set up our mask when we go to store. So if it's a byte, we're going to look at the address and determine how to set up the byte mask right here. This is going to determine how you're reading and writing from memory. So having said all that, we now know that when we read a byte or one of our registers out of our component, we need to uplift it, if you will, into a full 32 bits. So we'll take a look at that next. So here's where that memory mapping comes into play. We'll look at writing to our UART component first. So we know that the data that we're dealing with is 8 bits, and this is the data that's going to come into our UART. The Femto, if we know we're writing to the Femto is going to tell us which bytes that we need to write to the device. And in our case, we only need to select one of the 32 bits of data coming from the Femto and write it into a single place inside of our UART data channel. This is the wires that go directly to the UART itself. So we look at each mask bit and select which one of the bytes that we want to write into the UART. If you don't do this, if you assume that the Femto is going to give you the lower byte of the 32-bit word, that would be wrong. 3 out of 4 you would get wrong. So you need to look at the mask so that we can correctly route one of the bytes into our UART. Now, for reading from it, this is the mistake one of the issues I ran into at first. Ironically, I told you that we need to look at which one of the bytes. Originally, I actually wasn't looking at the proper bytes when I was reading from it. I don't know what I was thinking, but originally I would take the data coming out of the UART, if it was a control register or the receive buffer, and I always assumed that it goes into the lower byte for the Femto, and this isn't correct. And I'm going to show you the memory map again so that we can see why it isn't correct. You can see that in the memory map we have each one of our address registers at a separate word address, but we're taking the byte and we need to move it. For example, if it's at this address right here, this is a byte out of our UART, but it needs to go into the second. So each one of these 4 addresses here is actually considered a separate byte in the word itself. So if I come back to the UART here, to the code, and we take a look at our code right here, I was making the assumption that this data coming out of the UART always goes into the bottom end and that I fill in the top portions with the 0, and that's wrong. We need to actually look at the address, so I'll uncomment the code back to its correct way and look at the address and say, oh, it's address 00. We need to take that and place it in the lowest byte because Femto is going to see it aligned to the 0 address. If it's at a 01, if we're reading the 01 register in our UART address, we need to actually put that data right here because, again, the Femto will see the UART component as a single byte, if you will. It's at 4 different locations in memory, but they're spread out 1 byte at a time. So with that in mind, we can grab and place our UART in its appropriate position. So we're just moving. It looks like it's lined up in the same place, but it's not. It's actually 8 bits over here and 16. Then we push it a little bit to the left by padding to 16 on this side and 8 on that side. And then finally, if we're looking at address 11, we push it all the way to the top. Now this was the bug that I had originally. I couldn't figure out why every time I would try to read the receive buffer, I would get zeros out of it. And that's when I realized that our UART component looks like to the Femto as a single 32 bits altogether, and each one of those is at a byte location. And this is what to know about the RISC-V, and we've covered this in my other videos, is that the RISC-V is a byte aligned device and it is set up in little endian format. So the lowest address contains the least significant byte. And you need to really keep that in mind or otherwise you'll be confused. So this address is important and the mask is very, very important as well. Before we take a look at the UART component HDL code, let's take a look at the simulation first. And by that, I mean we're going to take a look at a very tiny portion of the simulation. It's just too much information and it would make the video extremely long. So here we are in the simulation, and if I scroll to the top, you'll see the main clock, and as you can see, everything is pretty much solid, and that's because there's a lot going on. There's a lot of clocks going on. What we're interested in is the read strobe over here, and in order to see it, we're going to have to zoom way in on the read strobe. So if we zoom in, we can start to see various addresses and states transitioning, and let's continue to move in on it. And this is what we want to look at. We want to see this instruction right here, which is line 29 up there in the code. And that's a store word. So what the read strobe is technically what it isn't. We shouldn't expect to see the read strobe itself. Now again, the read strobe is indicating the beginning of a read cycle. And this allows devices to sense the strobe, then go into their own state machine of some sort and potentially respond either immediately or after a certain period of time as to whether they're busy or not. Normally the read strobe would go high. If the device felt like it was slow, it would raise the busy flag itself and keep it high until it was done fetching the data for whatever reason, and then it would bring it back low. Now in our case, the The BRAM, the block RAM, is pretty fast. It doesn't have any really wait cycles when it comes to working on the FPGA. If you crank your clock up high enough, I think you'll start to violate some of the timing constraints, but we're pretty low. So in my case, the component just keeps the busy flag low. We're never busy. Whenever they want something, we got it. And that's what this instruction store word is doing right here. And because it's a store word, we expect to see the mask to have all the bits set to 1, because we're not storing a byte or a half word, we're storing a full word, which is all the bytes. So that's good. We're seeing exactly what we expect to. We also know that the address is in the RAM location, so that's good. We shouldn't see, if we come down here to the memory address, yeah, it's indicating that it's RAM, so it went high. So that's good. Now, an actual read strobe cycle happens on the very next instruction, which is a load byte unsigned. And sure enough, the read strobe triggers off. And our code simply leaves the busy flag low. It pulls it low and keeps it low because it's always going to be ready to div out the data. And this is what I wanted to cover in terms of the read strobe. There's a lot of stuff, as you can see, going on in here. And we've covered this before, but I wanted to cover just the read strobe because it's very important for your devices when you're reading. Now the write has a slightly different characteristic where instead of a strobe, you're literally detecting an address, a chip select, and then you can see the write flag come out of the processor to indicate whether you're reading or writing. I just wanted to cover the read strobe real quick so that we knew what was going on with it, and that's it. With that very, very brief look at the simulation, let's take a look at the HDL and specifically two of them, the UART and the SoC. So here's the UART component that we're going to interface with our Femto inside of the SoC. We have the clock coming in, the reset, our chip select, and here's that read strobe that initiates a read cycle, whether we're busy, how long it's taken us, or we're going to do a write. This is the bit streams coming into and out of via the real device world. What address we're going to talk to inside of our component. This would be the bytes that are coming into and out of our component. After they've come in serially, they come out in parallel here. We'll ignore the interrupts for now. Here we're looking to see whether we're active with our write and whether we're trying to write to the control register, which I do almost pretty much none in this particular video. Whether we're writing to the transmit buffer, and we do that. And we are also looking at determining which one of the bytes that are coming in are routed to the different buffers, either routed to the control register or the byte. We're looking at our receiver. Originally I was using a MUX for that too, but below we'll take a look what I did. Here's our transmit and our receive components. These are connected to the bit streams that come in from the USB to UART and then output a complete byte for our SoC to go into one of the buffers, the receive or the transmit. And here we are at the state machine. We got our usual resets and everything, and then we go into device idle. In this case, if the chip select's activated and we're starting a read strobe, we'll launch into a begin cycle. The busy flag constantly held low. That's what we'll see. We'll go into a read, and when we're done with the read, then we'll go back and do an end and then a device cycle. The transmitter, when that's activated, we'll go into transmit state. So the combinatorial section is pretty much just controlling, for the most part, the states. Occasionally I've got an enable bit for the transmission. So if we're transmitting, we'll hit this idle first, we'll then move to transmit. This state here will load it. We'll see that in the synchronous section. And the same thing for the receive. We're going to go through our states and look to see what we're doing. If we are in idle and a byte suddenly comes in, we'll set a flag. In this case, I'm not using interrupts, but I did it for completeness for now. We'll trigger an interrupt, and then we'll move through it. So this section of it is just pretty much, for the most part, is the state control. Now we'll look at the synchronous, where a lot of it actually happens. If we're writing to the control register, we'll take that control byte that came in and put it in our control register. So you'll need to pull it out of the control registers, mask things in and out, and then write it back in. This is a typical way a controller will work. We're doing a reset, setting all of our buffers. Now here's that begin read. We saw that the RX was selected, so we'll take the receive buffer and move it to the output. Now the SoC can actually see that data and read it. And of course, we've set our busy flag to none. It's immediately and instantaneously 0, and it stays that way. Then we come over here to the end. We look to see if we're still in selected, and we clear that received RX value. Again, when our assembly code reads the control, the component itself will automatically clear this flag. This flag gets set down here when a byte has come in. When the assembly code reads it, we clear it out. And the same thing for a chip select and row. We set our busy flag temporarily to a 1, and then on the next clock cycle, it's immediately set low. So it's basically, it shows up as low all the time. Okay, so if we're in the transmitter state and we're left idle, as soon as a byte comes in, we take it, throw it in our buffer, set that flag that we were clearing up above, and move on. For the transmit complete, we set our busy flag to 0. So that's the other end of this idle state right here, and that's it. The receive is roughly the same. A byte has come in from the receiver, and we place it into the receiver buffer, and we set this flag equal to 1. So we've got a couple of flags, the TX busy. In other words, we don't want to try to send a byte while it's in the process of sending another byte, and we don't want to try to read a byte if it's in the process of reading a byte. That's it for the UART component. So let's take a look at the SoC. Again, the usual thing as we interface to our ports and everything, this will connect to the top, our PIL, the RAM as usual, and here's where we're detecting that mask and determining which byte we're going to write. So if we're only writing a byte, we don't want to wipe out what's in the other bytes. We only want to wipe out or overwrite the byte that has bit. Now if you're doing a half word, 2 of these bits will be set, and you'll overwrite either this half or that half. And of course, if they're all set, you're going to overwrite all of them here. And that's how the RAM portion of it works. This is our firmware that we're loading. We've seen that before. We've got all of our I/O devices. Now this section is taking that memory map granularity that I showed and breaking it down into its address and its device. And then we look to see whether we're writing to port A. So we say, hey, is it an I/O address and is it port A? Then we're writing. If that's the case, then again, we have to look to see what the write mask says so that we can pull out the correct byte out of the 32-bit word and put it into port A. If we come down here to the UART component, here we are. We're interfacing all of those signals coming from Femto, coming from the UART component, receivers and transmitters, and we're binding them all up. Here we're looking to say, hey, are we trying to write to the UART? Okay, again, just like in memory, we have to look at the masks and find out which are the byte that we're trying to write to our UART and pull it out. Again, this all has to do with the fact that a word sits over 4 byte addresses, if you will, because memory on a RISC-V is byte addressable. It's not word addressable. Word addressable in RISC-V is more of a virtual thing, and it shows up mostly in your assembly and in firmware, but RISC-V standardized on byte addressability when it comes to storage. And that's exactly what we're doing. We have to obey that by looking at that write mask and determining what we're going to store in that particular byte in that location. And the same thing for here. We're looking at the appropriate, we covered this before, and we're also looking to see how we're going to read data out of a specific address. So if it's an address that sits at 01, we're not going to look at that lower byte. We're going to look at the next byte over, and so on and so forth. Here's the CPU. That's the Femto right there. We got it all hooked up with the interrupts going. We're not using them yet. And then that's it. And then the final thing down here at the bottom is that the PLL takes time for it to stabilize and come up. So I threw in a really cheesy counter that just literally counts for like 250 milliseconds, but it only takes like 50 milliseconds for the PLL to come up. And the one thing that I did learn is that I added a reset button to my SoC. And you do not want to reset that PLL once it's been come up and stabilized. You can set it, but I'm not doing it right. There's a specific sequence you have to follow to properly reset the PLL, and I wasn't following it. So I just simply don't reset it. When I reset the processor, I leave the PLL alone. Having said all that, we're ready to synthesize. In order to do that, we need an assembly program. And I happen to have one right here, the Monitor Echo Stack program. All it does is it grabs the byte that was sent to it by a Go program over here to the right and spits it out over here into the terminal that I'll show you in a minute. So starting at the top, I'm not going to go through this in great detail. It's a lot of assembly code, but we'll just cover the highlights. Most important thing is the base of port A and the base of UART. We need those to write to. And I've also gone ahead and played around with the stack as well here. This is not following the ABI. I'm sure it's some other register you're supposed to use for the stack, but X11 was a number I like. We also spit out the word OK when the program starts up. We clear out port A, and then we go into a big loop that is polling for the receive flag. Now remember in that diagram I showed the bit that is set when a byte comes in from the hardware? This is polling it. So it jumps down to this subroutine right down here. It first pushes X1 onto the stack, then it enters into a really tight loop of reading the control register. Here we're loading byte X2 points to the base, and the control register is at address 0 within that component. Then we AND it with a mask because we know that the bit that we're looking for is the bit that indicates a byte has been received. And we go around in circles, and then finally we pop X1 back off because we're destroying it here. We want to save it here and then restore it right here, and then we return. So if we come back up here, we'll see that we'll finally fall into here. We'll load X1 with whatever came in on the receive register because the bit is telling us so. We'll echo it out on the byte, our LEDs, and we'll echo it back to the terminal using our print character routine. And that one is down here. It just simply takes whatever's in X1, sends it to the transmitter, and then waits on it here. And then we return back when we're done, back up to here. We now check the character that we received, and if it's a 4, we do end of line of transmission. That's the ASCII character for end of transmission. And then we go to exit, which simply prints out another string and exits. Otherwise, a carriage return, we also echo back a line feed so that not only does the cursor go to the left, but it goes down as well. And then we go back into a loop. And that's it. So we have all of our routines down here for doing those things. And then finally we have our data section. Here's the base of A. Remember on that memory map, this bit here, 4, is going to set and tell us that we're dealing with I/O. We also need to do it for UART, but we also specify the UART device. This is specifying port A as the device, and this one specifies the UART. And then we have a couple of our strings, and the memory is little endian format, so the lowest byte is where the first byte of the character starts, and then we keep going upwards in bytes. So memory is increasing this way from left to right, and growing and growing and growing. The stack, however, I picked it far away from 5.0, grows in the opposite direction. I purposely have decremented the stack pointer here, then we store something in it, then we pull it back out, and then we increment, putting the stack pointer back to its topmost position. And that's it. We're ready to rock and roll. Let's take a look at the terminals and get those up. And the first thing we want to do is assemble that program right there. Then we want to bake it all in with the program, and while that's doing it, I'll bring up the actual video capture of our card. There's the top Schoko right there, the Tiger's up there. There's our USB terminal here, and then finally we have over there to the left is the LEDs. Okay, so the little LED on the Schoko is green, which means the program is running. I need to review that and show that to you as well, so we'll do that afterwards. So now that we're ready to go, we can come over here to let's move our capture out of the way here now that we've compiled, and let's start sending characters to the program. We'll send the number 1, and we should see up at the upper top the word OK. The program has come up, and now we see a 1 up there, up at the upper top right there. Excellent. So we'll send a 32, which is ASCII for the number 2. So now we see the number 2. Now we'll send a carriage return, which is 0D. And you should see the caret go to the left and down immediately, instantaneously. That's because the program is recognizing it. And there you go. It worked. It actually recognized the carriage return and spit back a line feed to us. It's fine. We can keep going and adding in different numbers. 35, 45 will give us the capital letters and things, and we can go even bigger with 66, I think, is the lowercase f, so now we're in there. And now we want it to recognize the end of terminal. So we'll send an 04, and it should tell us the word bye. And it did. There's the word bye. Excellent. So our assembly program and the RISC-V, our SoC, is actually working through the UART component, doing everything it needs to do. So you can see that our LED over here has been showing us everything, and the little light down here went red, meaning it exited out. So let's take a look at the SoC again, and one of the things I wanted to mention real quick is that LED on the Schoko and how it's set. So we have it detecting the halt flag. If it goes high, we set the red light on and we let the rest of them go off. And then when it's running, the green light is on. So if we were to switch back and turn on our program, if I hit the reset button, we should go out of the halt state and rerun the program. So I'll put my hand on that, hit the reset, and sure enough, the light is now green. So if I turn around and send, you can't see in the terminal, I'll send the 04 again, it'll turn red. So the program is working as expected. Excellent. Nice. We now have a basic form of communications, which adds another component to our retro-ish computer SoC. In the next episode, we'll cover building a monitor and implementing a software control protocol versus a hardware control protocol. I'm not sure how long this will take. I do have a vacation coming up, so I'm hoping it takes less than a month, but you never know. But just keep an eye out, and otherwise, so until next time, peace.